about WhizBiz.com, and how nice that you want to follow along with this project, building my ultimate multi-power module. And this is part 3, in which we're gonna finally build everything together. So I'll let you take a look over my shoulder in designing and printing a case for the module and the PCBs that are gonna make this module. This is my Zauberling. I hope you remember it from a previous video. Take a look at my timeline there. And because the installation space is ultimately only 3.5 by 7 centimeters, I had to split the printed circuit board into 2 layers that can be sandwiched together like so. And designing a PCB sandwich like this is always a great challenge because the gap is only 11 millimeters, and you have to make sure that parts of the bottom of the PCB do not collide with high parts on the bottom PCB. For this project I also need a relay like this, and the problem here is that this single component is already higher than 11 millimeters. But I think we can tackle that by just lowering those small rims at the bottom of the casing a little bit. About 1 millimeter will do the trick. So we can gain that extra height in between the PCBs without having to raise the front or such. Another thing is these voltage regulators. There are 2 big voltage regulators, the rest is SMD type, on the PCB. And because they might develop a little heat in one of my earlier prototypes of the Zauberling, I solved it like this, and I mounted them on the back of the casing with a little heatsink on. This new power module, however, does not need an external I2C bus connector on the back, and the programming port does not have to be as easily accessible as on the Zauberling. After all, the firmware will not change very often. So these holes are not there, and that leaves us space for the 2 voltage regulators. If there was an opening they could poke through, we could even attach a passive heatsink at the back of the module to cool them, if that would be necessary. Even if they don't develop any heat, it would always be good to have them outside the casing, wouldn't it? Eventually, I'd like to have a easy accessible on-off switch and a DC connector in the box, in the casing, so we have to consider this while designing the lower PCB that's in there, because these elements are protruding a little bit into the casing, and we have to take that into account when we're gonna design the PCBs. But first, let's take a look at the casing. Here we have our original Zauberling casing, and because this is a power supply module, it will mostly be used at the far left of a series of Silberlingen or Zauberlingen. So it will be the leftmost module in a row. This means that this side is available for connecting the DC adapter and the easy accessible on-off button, of course. So we have to make a flat side on this side, and once we have it, we can easily digitally drill the hole for the switch, for the on-off switch, and we can drill a hole in the 3D print for a DC connector. So we have 2 new holes and 2 existing holes. These are the 12-volt outputs at the back. Let's drill a new hole for those 2 voltage regulators there, and perhaps insert a kind of a rim to rest their heat sinks against, like so. So the metal parts of those voltage regulators can rest against that and leave the back of the module completely even for a possible heatsink. Okay, there we have it in wireframe. Hope you can see what my idea would be. Hope it works out in the 3D print. We'll see that in a moment. So after a little work in KiCad, I came to this for my bottom PCB number 1, the one that's on the bottom of the case, that contains the INA current sensor and the voltage regulators. And it was quite a challenge to position everything in such a way that it doesn't collide with the elements on the top circuit board, or the switch or the plug that protrude inside the case. Here we are in KiCad's routing module, and as you can see, I used quite a few vias to get it designed, and I deliberately kept the track width of the tracks of the output voltages as wide as possible. Here they are 1.5 millimeter. That should easily handle up to 2 amps, I guess. For now, I've simply opted for 1 ounce of copper, but you can increase this to 2 ounces, or you can keep the traces open in your solder mask so that you can completely tin them in with solder. None of this is necessary for the currents that I expect with my experiments. A quick look at the top PCB, the one containing all the buttons and all the front elements, like the voltage rails, the display, and of course the microprocessor, the Arduino Pro Mini, on the back. These are power rails for 12, 9, 5 and 3.3 volts. There are a few LEDs on there that signal which mode is displayed on the display, and 5 positions for the SMD style push buttons I have to solder on there, a LED for the automatic fuse, an FTDI connector to program our Arduino Pro Mini. We have connectors. This is the main power rail with all the voltages that go to the front. We have a critical and a fuse connection. Of course, the I2C, and this is where the 9 volts come in, and the 5 volts made by the Arduino Pro Mini voltage regulator go out to the bottom PCB. Okay, so let's take a look at my freshly designed and printed 3D casing with a thickening ring for the DC connector there. Let it protrude a little bit more outside. And here we have our window for 2 voltage regulators with a small, what we call it, a small threshold to lean against, leaving the back completely flat. I think this is gonna work because it's completely flat, we can attach a passive heatsink like so. And with the DC connector, this little ring will save us a few millimeters inside the casing. There is room on the PCB to accommodate this switch. So there you have it, a new incarnation of the Zauberling casing with a flat side. So after a bit of waiting, I got this, my printed circuit boards. This is the lower PCB with almost all the SMD components already placed. So all I have to do is place some through-hole components to really finish it. Unfortunately, there was a mistake made by me. I mistakenly removed one of the components from the bill of material. The 3.3 volt voltage regulator is missing here, so I have to hot air solder that in myself. And there's another thing, I have to make a connection here. Unfortunately, 2 of the vias, look at this isolated trace that has no vias. There must be vias inserted here, just like the ones over here. And they are in fact placed by me in KiCad, but they didn't show up in the drill file, so I have no clue how that happened. I'm recommended for any tips if some of you know why this apparently happens. So let's take a look at the top PCB. Not much going on there. I have to hot air solder some resistors for LEDs on there, 4 of them. And the rest of it can be quite easily semi-SMD mounted, like this Arduino Pro Mini board on the bottom of this small PCB. So just take a look at my Zauberling video down my timeline here to learn more about this height-saving mounting method. Is that a word? I hope so. Okay, we're all done. This is my lower PCB with my fixed connection and my soldered voltage regulator over there, and the rest of the components is already mounted. I omitted the fuse and the switch, and also the DC plug, of course, is not soldered on there yet, but this gives a good view of the INA chip with its shunt resistors. We have our connectors soldered on, so everything is in place to give this PCB a little test drive. This is our I2C bus, so to test this little thing we could do exactly the same we did with the breadboard testing. I've got my voltage regulator in place for the moment, so 5 volt has been produced for the I&A chip, and we don't need the top PCB yet, so let me connect this thing. First of all, our 3.3 volt is coming out here on the first, and the second one, yeah, very nice, 5 volt for that one, and we have 9 volts over here, and this is just the DC input voltage of around 12 volt. Voltage regulators on the back, they'll be poking through the bottom of the case in a moment. Once we have built in this little PCB, they'll be sticking out at the back. And let's see. Let's check this 9 volt coming in our temporary voltage regulator and 5 volts going out. So the I&A chip must also be powered up with the correct 5 volts. Let me see if we can read it. And hey, presto, it worked right away. And when we pull the yellow I2C bus like so, it just reads zeros. That's one of the characteristics. An unconnected I2C bus just returns zeros, which is different from a completely not powered up I&A chip, because when we pull our temporary voltage regulator here and omit the 5 volts to the I&A chip, you see that it hangs and it just goes on when we put it back and give it 5 volts again. Okay, let's take a look then at the top PCB with the front elements. Arduino Pro Mini hanging there on the bottom, piggyback style, and on the front of course all the elements that we want to bring through the front. This small custom printed 3D stub goes underneath the display to mount that to the correct height over there. And I hope it will fit. Let's see if it fits. Of course, I already tried it out. Ha ha ha. There it goes. And by the way, I already flashed the sketch into this top PCB so we can immediately test it. As you can see, there's a little gap because the relay is a bit too high. There's a small gap in the connectors here. No problem, because we've sunk the bottom PCB a little bit more into the case. So nothing happens on the front there in terms of height. And as you can see, there's little room. So it's very crowded there, but it all fits very snugly into the tiny space within the casing. So we're quite efficiently using the height and all the space that we have in the case. I just can't wait to test it. It is initializing its screen, as you can see, and there it is. It's displaying the first voltage on its display, which is the external 12 volt. And we can go to the next step, which is displaying the 9 and the 5 volt. Of course, the 3.3 is not displayed, but we can have everything on one display and we can reset the whole module. You can see, I hope you can see, the little blinking LED signals a initialization phase for the relay and the automatic fuse, like so. So this is fully functional. And well, there we have it. One comprehensive module providing 12, 9, 5 and 3.3 volts. Let's see if all these voltages are really there. This must be the 12 volt input. There you have it. And this 12 volt coming from the external DC adapter, of course, is also passed to the back of the module, so you can loop through it to your other Silberlingen or Zauberlingen. Yes, that's okay. And while I go on testing the other voltages, this is a great time for you to subscribe to my channel should you like these videos, or should these videos be of any use to you with your own electronic projects. Next step, building it all in. So as you can see, I've already inserted the two voltage regulators in their window in the bottom of the casing, and there goes the lower PCB. Fits nicely into the box, and with the two 12-volt connectors protruding through the bottom, there you go. Voltage regulators on the back, completely flush with the surface of the back of the modules, enabling an external heatsink, optional of course. And as you can see, I already have the DC connector and the switch in place, and I've connected and soldered the sides strips of the module, and we're almost there. Just by inserting this PCB, this top PCB with all the front elements on it, we're almost ready to test. Let me show you my laminated and 3D printed front here. Here's one I've prepared earlier. Always wanted to say that. And it just fits over the front elements on the top PCB, like so. So let's connect some power and see if it works. Well, it looks like it. There it goes. Displaying the different voltages. We can cycle through the display. And before we conclude this final part 3 of this video series, let's give it a test with the motor again. Automatic fuse of 12 volt kicks in at 1.5 amp at the moment. Let's lower that a little bit under 100 milliamps and see if it really works if we hold the motor. For instance, 80 milliamps will do. I'll hold the motor, and there it goes. The automatic fuse trips. So that's tested and everything seemed to work very nice. So this concludes my quest for my ultimate multi-power module. It's great that you have watched the development of this useful module so far. You'll find all the information in the comments of this video. And if you like it, subscribe to my channel. I'm looking forward to seeing you with my next project. Until then, happy hacking!